Picture this. You're in a spacecraft falling toward a black hole. The onboard computer is counting down to the point of no return. 3, 2, 1. Nothing. No impact. No flash. No boundary outside the window. The instruments hum along. The drop of coffee floating in front of you doesn't even tremble. But you have just crossed the event horizon, the border that nothing has ever come back from, including light. How can you cross the most terrifying border in the universe and not notice? Today, you'll learn why small black holes destroy you thousands of kilometers before the entrance, while the biggest ones let you in without a sound, and how much time you have left after crossing, before the tidal forces finally catch up with you. First, what a black hole actually is, and forget the cosmic vacuum cleaner. If the sun turned into a black hole of the same mass right now, Earth wouldn't budge from its orbit. It would get dark and very cold, but our path around it would stay exactly the same. From a distance, a black hole pulls exactly like a star of the same mass, no more strongly. The real danger begins when you get close. Every black hole has a border, the event horizon. And here's what matters. It's not a surface, not a wall, not a membrane. There is nothing material there to touch. It's a causal boundary. Outside it, you can still turn around and leave. From inside it, no signal, no ray of light will ever get out again. Astronomers call it the point of no return. And every black hole's border has its own size. The more mass, the wider the horizon. Remember that. That's exactly where nature hides the trick. Sounds like the most dangerous place in the universe? Well, this is where things get strange. Take a stellar mass black hole, with 10 times the sun's mass. Its entire horizon is a sphere just 59 kilometers across, the size of a single city. So it seems like you could fly right up to the edge and peek inside. You can't. Long before the horizon, you'd meet the invisible weapon of black holes, tidal forces. Your feet are closer to the black hole than your head, so they get pulled harder. That difference exists right now. At this very second, your feet are being pulled toward the earth slightly harder than the top of your head. It is far too small to feel. Near a small black hole, everything changes. Thousands of kilometers before the horizon, that tidal difference already becomes lethal. And closer in, it starts stretching you, and your ship, into a long, thin strand. Physicists have an oddly casual word for it: spaghettification. You would never reach the border in one piece. Small black holes don't let guests anywhere near the door. But here's the truly strange part. The bigger the black hole, the gentler its horizon becomes. That sounds backwards, right? More mass, stronger gravity, a deadlier border. No. Here's nature's trick. Mass increases the pull, but the horizon grows with it, so at the border, you end up much farther from the center, which means the difference in pull between your head and your feet at the horizon doesn't grow. It shrinks. As the square of the mass, double the mass and the horizon doubles. But the tidal difference there falls by 4. Make the hole 1,000 times more massive, and its horizon becomes 1,000,000 times gentler. Now, take a giant. At the center of the galaxy, M87 sits a black hole with the mass of 6.5 billion suns. That one, admittedly, isn't asleep. It's surrounded by glowing, superheated matter. So picture its quiet, non-spinning twin instead, the same giant in an empty corner of the universe, dormant, no fire. The diameter of its horizon, 38 billion kilometers. Inside that sphere, the orbits of every planet in the solar system would fit, including Pluto. That diameter equals the distance light travels through empty space in almost a day and a half. And the difference in pull between your head and your feet at that border? About 20 billion times weaker than the gravity you feel standing on Earth. Completely imperceptible. You experience more just turning in an office chair. The giant black hole greets you with nothing. So now you're falling toward the dormant giant. What do you see? The sky starts behaving strangely. Images of stars stretch and double, like a hall of crooked mirrors. You see the same stars 2, even 3 times. The giant's gravity bends their light like an enormous lens. The light ahead grows brighter and whiter. You're moving so fast that almost the entire sky squeezes forward toward your bow. Why no alarm? Because the horizon is a global boundary, not a local shockwave. You, the ship, and the floating coffee are all falling together. Instruments can measure tidal differences, but at a giant's horizon, those differences are still tiny. The computer counts again. 3, 2, 1, horizon. And again, nothing. No jolt, no flash, no sudden change in the instrument readings. If the computer hadn't calculated that point in advance, you would not know you were already inside. The horizon is not a material boundary you can feel. In your immediate surroundings, nothing special happens at the crossing, but something has already happened, permanently. The radio message you send right now will never leave this region. And outside, a distant observer never sees you cross at all. Your signals arrive farther and farther apart, redder and fainter, until the image of your ship fades out against the black. 2 witnesses, 1 event, 2 radically different stories, and both are true. But that's not the whole story. Inside the dormant giant, it's quiet. Too quiet. The border is behind you. So what now? Now comes the eeriest property of black holes. In the simple non-spinning model, a route that leads outward and forward in time no longer exists. Your engines work. You still have fuel. But every possible path into your future leads deeper inward. Think about that. The center is no longer a direction in space. The center is your future. Turning the ship around and flying out is as impossible as waking up in yesterday. So, how much time do you have? In 2024, NASA astrophysicist Jeremy Schnittman simulated one such trajectory on a supercomputer, frame by frame. This visualization produced 10 terabytes of data and took 5 days on NASA's Discover supercomputer. A normal laptop would have needed more than a decade. The model, a non-spinning black hole with the mass of 4.3 million suns, like the one at the center of our own galaxy. The radius of its horizon, about 12.5 million kilometers. The camera crosses the horizon. No impact, no visible border, just as relativity predicts. And then, 12.8 seconds later, tidal forces tear the camera apart, roughly 128,000 kilometers from the center. After that, the final stretch is over almost instantly. 12.8 seconds. That's how long the camera survived inside the horizon before it was destroyed. Inside the same simplified, non-spinning model, a quiet black hole as massive as the one in M87 could give you hours rather than seconds, although the exact time would depend on your trajectory. But the ending does not change. Spaghettification simply waits on the other side, where no outside observer will ever see it. And what does the universe see? Only a dot that reddens and fades. No flash at the moment of crossing. No signal sent after the crossing. The black hole just becomes imperceptibly heavier. The loudest event of your life passes almost without witnesses. We picture black holes as monsters that tear and swallow. The truth is quieter and darker. The small ones do tear, but the biggest ones let you in so gently that you'd miss the moment after which everything is already decided. The outside universe may watch your last light fade, but it can never receive a message sent after you cross. 3, 2, 1. And without the countdown, you would never know when it happened.